All right, welcome back, everybody. I'm going to finish up this module that I've been on for the last couple of lectures. I did have a little bit more that I wanted to show you there, and then I'm going to transition this course to a series of lectures on the theory behind FEA. Let me project my slides on the screen, and I'm already sharing them for the benefit of anybody who watches it later on Zoom. Here we go. Okay, so last time we finally got to understanding how this instrument works. And as a very, very quick recap, before I move on to the last slides. So it's taken 3 lectures to come through this presentation, and it takes time to digest these things. But last time we finally made it to understanding or applying our theory, or a general understanding of the theory, to how the commercial laser vibrometer works. And this cartoon does some reasonable job of representing what the equations tell us. There's a little bit missing. What's missing is the output of that photodetector. The output of that photodetector gives the time averaged response. And what we saw from the derivation is that the time averaged interference signal that you get doesn't have the electromagnetic frequency of light in it any longer. Okay, that aspect of time is gone. And what we're seeing are essentially either a stationary standing wave pattern, which we call a fringe pattern, or if our fringe pattern is being modulated because of motion, those fringes have a temporal character to them. Okay, now this Bragg cell was the magic behind how this device works. It was the thing we inserted in one of the beams that the other beam didn't have, and it placed a frequency on the signal. Whether we were moving, whether our surface was moving or not, you ought to imagine that the output that this device is registering, if you were to look at it with a Fourier transform, there'd be something like a 40 megahertz constant signal on that interference signal if our sample wasn't moving at all. Okay, this is what literally would be on there. And the benefit of this Bragg frequency is that now, let me shift to the next slide, try to emphasize it. Here is the key result, okay? It says the interferometer's output, if we're treating it as a velocity interferometer, says the phase portion that's being reported is 2 pi f Bragg. Yep, that's this. That's FB, F Bragg, that the Bragg cell puts on. And U dot is the velocity of the surface. If U dot is 0, then what it sees is just nothing but the Bragg frequency on the signal. Now, if the surface that you're reflecting light from begins to move and has a U dot, then if that U dot is positive, that phase FB minus 2 U dot over lambda. By the way, no one asked me what alpha is. Alpha is, well, let's say we approached our sample with a vibrometer and there was a small angle of incidence, alpha, that we came in with and came out with, okay? Say there's a small angle of incidence. There's a very, very tiny cosine correction. If this angle is small, cosine of alpha is very nearly 1 anyway. I'm just putting it in there to be mathematically complete. This is the key. If the sine SIGN of UD is plus or minus, then the sign of that phase term, which I'm calling omega S here, is going to either shift to the right or to the left of this Bragg signal. And when you do the FFT analysis, and they do it for you, you buy a commercial device like this, you don't sit down and take the data and do FFTs. All the hardware and software you're buying is doing that for you. It is doing fast Fourier transforms, and it is figuring out where is your signal instantaneously, okay? And as that frequency of that signal varies, the net frequency of this signal translates immediately into the velocity of the surface, okay? And it can detect now whether the surface is moving toward you or away from you. This is called heterodyning. I wrote the word once, and I just want to mention it. This is how you get out of this ambiguity of how do I know if my surface is moving forward or backward, okay? It's a very important aspect of interferometry, and it's done for you with the benefit of this Bragg cell, and you could read about a Bragg cell and how it works, okay? Bragg cell is able to put this characteristic frequency on the signal. All right, so that's the laser vibrometer. Now, let me show you some applications of this cool device. This was one in the laboratory that I did last year for ME50B. There's this beam vibrating. There's a laser vibrometer pointing down, way down near the clamping position of the beam. This is an actual signal coming from the vibrometer, all processed for you in real time, okay? That's a damped signal already processed instantaneously. Here's the zoomed in view. There's the laser beam focused just behind a strain gauge that I had on the sample as well. And then up, I'm trying to just sort of show you where the vibrometer is sitting, looking straight down on the beam. And then I'm just going to pan around the room and maybe show some other aspects. This is a nice close-up view again. By the way, this is the retroreflective tape. Really helpful to put that tape on there whenever you can. It really aids in the amount of light that comes back to the device. All right. That's just the iPhone freaking out, trying to focus on that light beam. So sometimes it defocuses, sometimes it doesn't. Again, the signal that we get out automatically registered. And then what you do with this in the vibration world is you take Fourier transforms of this data, and you try to identify these sharp peaks in your data. And those sharp peaks are resonant frequencies of your structure, okay? Right, so you get out this modulating signal, but contained in it are these various, now this is just the pure F Bragg signal. The actual signal you'd get if your surface was moving would be this plus other things, right? And so you have a lot of frequency content inside here in this burst, okay? This is me flicking the beam, it vibrating and then damping out. And then I flick it again, and it vibrates and damps out, okay? And so all that is the vibrometer kicking out. There's amplitude, velocity versus time, or displacement versus time, and contained within that is the frequency content. You have a question, Jedi? That's right. These are time, and you can think of this amplitude as the velocity of the surface. That's all being pumped out to you when you buy a commercial device like this. But the magic of how they did that is all the theory I've discussed, okay? So you get out onto your computer screen, velocity versus time, if this is what you selected in the menu, right? And it knows how to process and count the fringes, if you will, do the FFT analysis on it. Now, this is just a spectrum where we say, hey, give me a spectrum of this signal. If you were interested in decay time, you could certainly look at this decay time and look at the damping characteristic of your structure. That's a very valuable thing to study. Okay, we want to know how quickly things quiet down, right? Another thing then would be, what are the dominant modes or frequencies present? Okay. All right, so that's just an example. Let me kind of give you a tour now. This is a device, this is a vibrometer, another one. It's just a faster one, and it has a fiber optic output. Very, very useful, okay, when you're trying to snake this light beam into a very difficult location that you want to probe. If you have some way of holding that probe in space, you can sneak it in, shine light off of that part of the structure, and pump it back into your device. All the optics are in this box, right? Because it spits the light out through that fiber, connects it back through that fiber. This is a pigtail, so you actually get two outputs here. And then all the interference goes on inside the box. Here's the Bragg cell. And then you have to get this controller that talks to this, takes all the signal that this diode produces, processes it, and then kicks it out to your computer or oscilloscope as a processed velocity time signal. Okay, completely processed for your benefit. Okay, and they tell you so many volts on your oscilloscope will be so many meters per second. And you literally have that data. You can bring it into MATLAB, do things with it. So you're not having to do the interference analysis yourself if you buy a commercial system. Just like with strain gauges, we're not doing the strain gauge analysis, right? We went into the lab, we plugged in some strain gauges, and out came these process corrected signals for us, right? If we wanted to, we could even have the Vishay software compute the principal strain. And I think I demonstrated that to everyone, right? But then as an exercise, you had to do it yourself, right? Okay, so that's the idea behind that device. Now, I happen to use this particular device. I don't know how well this is projecting, but this is an experiment. Let me try to explain it because I know it looks rather busy. This is a hydraulic press. I don't want to go too deep into this, but I want you to appreciate what's going on here because there's a lot of interferometry in this picture. This is a hydraulic press, and you see this black frame that I'm encircling with my pointer, okay? That frame is holding this acrylic, think of it as an acrylic specimen. It's really made out of a material called Homalite 100. And if you look carefully, you'll see an interface, a seam between the two that runs diagonally. Can you see it from where you're sitting? So what this really is a fancy friction experiment where we've prepared two plates and mated them against each other. So you prepare these two separately, and then you put them into the press, and you have the press by virtue of friction. By virtue of the friction along this interface, these two plates are kept from slipping. Can you imagine that? Okay. In other words, if there were smooth surfaces, as soon as you push on them, you would think, gee, they'll just slide, right? But if these surfaces were prepared beforehand and roughened appropriately, and this angle was kept within a certain range, you can get static friction to hold that plate against that plate, okay? You're actually seeing it in front of your eyes, okay? You just don't see the load that's being registered, okay? And what happens in this experiment is, if you see carefully, you see this greenish tinge. Can you see that from where you're sitting? That's a big 6-inch diameter laser beam that's been expanded by that expander trick I told you about in a previous lecture, where you just pass it through some appropriate lenses and make a large beam, right? That then passes through the specimen, okay? And that light is processed by, I'll try to point to them if I can see them, polarizers that sit immediately behind this window that mix the light that has transmitted through in a way that will generate a fringe pattern, which I will show you in a future slide, okay? You don't see it, you don't see the fringe pattern because you see this camera back here? This camera is imaging that big fat beam that is passing through the sample, okay? It's being focused by this lens. See this big lens? Circular polarizer. Here are the polarizing optics ahead of it. Then that's being focused all the way down to this pair of fast, high-speed cameras that sit back here. So they're going to watch this stationary fringe pattern that we initially start with and how it changes as we make these surfaces slip. We're going to literally try to follow the rupture that travels along this interface associated with the failure of that interface to support the load. What we're mimicking is a mode 2 rupture. This is a classic strike-slip earthquake in the Earth's crust, where you have two plates and they slip. It's called a right lateral rupture, and that's literally what's being simulated in this experiment. Now you have to trigger it. There are details about that. You can't see it, but there's a very, very thin 80 micron wire filament that's passed right through here. The machine shop has to make a really fine channel for you that sits right there, and in goes this wire, and it comes out the backside, and it gets completed to a big capacitor bank, and that poor little wire cannot sustain that current, and it just flames out, okay? It just literally becomes plasma in a matter of microseconds, and that's enough to perturb these plates, to make them start to slip and nucleate the rupture. And the idea is in this experiment is to literally follow this rupture front as it advances along the interface, okay? It's like probing how two plates in the Earth's crust rupture, okay? Now, that's the full field picture, and I'll show you what the fringe patterns look like shortly. Simultaneously, I want you to see the red arrows that I've drawn in the figure, okay? And you notice how I've called one of them U1 dot, and another one U2 dot, and then another one U3 dot. So I want you to imagine on this sample, if you could have a retroreflective piece of that retroreflective tape we talked about, it's maybe just a couple of millimeters on a side. It's just a little chunk of that tape, taped very carefully right up against one of those seams, okay? Right up against that interface, okay? And the interesting thing is if we shine the light normally to that, we've been talking about for 2 lectures what we get back, right? We get back any normal component of motion, right? So when this rupture sweeps by, it's going to pass through here, and we're going to have the laser ready to detect something that sweeps by, okay? So then if there's some out-of-plane motion, the U3 dot would register that, right? Does that make sense, right? But we also want the in-plane motion. This is the segue to my current lecture. We would love to be able to measure this one. So I can't draw U3 on this diagram, but I'm going to show you, suppose we could somehow reflect right off the corner of this tape and get light to come back that way. Literally, we're almost grazing the plate, okay? So these beams are drawn showing you that we're almost grazing the plate, but we can't graze it. That's not possible, right? There's stuff in the way. We're coming in at a very shallow angle, and there's the vibrometer probe right here, okay, sending the light out. It's going to hit the corner of the tape, the retroreflective tape. By the way, this is a blow up of the tape, so you can see what I'm talking about, right? So you can see one beam comes in and hits that corner, another beam in plane hits that same corner coming from above, and then you could possibly even have U3 dot out like that. Okay, does that make sense? Okay, so you have another one that comes in like this then, okay? And I'm showing you that you can actually use these vibrometers in this very strange configuration that they don't even tell you about when they sell it to you, okay? Everybody's talking about using these vibrometers as, you know, U3 dot, right? Normal motion. But if you get that little retroreflective tape there and you come in at those beads, those little glass beads that sit on this tape, they do a phenomenal job of scattering light, and they scatter light back that way too, okay? So what we're able to get in this experiment then is the motion along, this is, the earthquake people would call this the fault parallel direction, okay? The fault, for obvious reasons, fault parallel component of motion. And this component here would be called the fault normal. And I just want to briefly go into this experiment. I don't want to turn the whole lecture into this, but it's an interesting application in the laboratory, okay? So you're going to try to obtain or simulate this motion in the laboratory and also the U3 dot, okay? That's the idea. So simultaneously, I want you to see how two interferometers are being used simultaneously here. I'll show you how they all come together. You've got the full field, which I haven't told you much about yet, which floods this sample with a big fat 650 millimeter beam and creates a fringe pattern that speaks to something. And I'll talk about that something once we see the fringe pattern, but put that on hold for a second. And simultaneously, we have these point measurement vibrometers measuring the motion very precisely as a point as this rupture sweeps by. I think the other ones on the side are just different perspectives showing the probes and the hardware that you use to hold the probes in space. That's the part you never think about, right? It's like, well, how am I going to hold these probes in space? You obviously need some machined bracket that's going to support these things for you and give you some little, you buy these mirror mounts at Newport or one of these optical vendors, and then they allow you to steer that beam very, very precisely. Otherwise, manually, it's very, very crude to try to position it on your own. So you've got these optical stages, if you will, that allow you to send that beam in and get that signal back, okay? Let me show you what happens now when we run such experiments. Now you can see some of the fringe patterns, okay? You can see some of the fringe patterns here. I want you to look at one on the left first, okay? The one on the left, I think even from sitting in the back, you should be able to make out this circular front, You see it? So this is the full field illuminating beam, okay? It's illuminating the entire specimen, and you can see this front. This is the shear wave, the S wave, the famous S wave you always hear about in earthquake mechanics discussions. The S wave is the speed of the speed at which shear waves propagate in the medium, okay? And this interferometer allows us to pick up that front. And then here I just annotated a little bit. And just behind that front, you see this butterfly-looking fringe pattern that I'm kind of hovering over with my pointer, and that is the rupture, okay? That is the leading front of the rupture. That's the singularity of this crack tip, if you will, that is sweeping down, okay? Sweeping down this fault. And up ahead, this material doesn't even know that it's about to slip yet, right? Because the time scale we're operating on, you've got this material here has already slipped. This material up here doesn't even know it's about to slip yet until this rupture gets to it and slips it, okay? This is what we're resolving, right? Rigid body slip is what we're taught to think about in everyday life, right? We think of two blocks just translating like this. But when things are stuck and are forced to lose that traction, there's literally a mode 2 crack, if you will, right? Mode 2 crack. There are three kinds of cracks, right? There are mode 1 cracks, right? That tear something open this way, right? That's a mode 1, right? But the mode 2 is literally, right? This one, where you're forcing the rupture, right, to go this way. Okay. And that's a class. By the way, yesterday in Turkey, it was a devastating earthquake. I'm sure you have all seen it on the news, okay? I'm sure you've all seen it on the news, okay? And the first thing I did when I woke up and I read about that earthquake was I went to usgs.com, because usgs.com has a live track of every earthquake detected all over the earth, anywhere, okay? And as soon as I scroll down to find the 7.8, which is an absolutely unbelievable magnitude for an earthquake, okay? The faults that this earthquake was generated from are classic strike slip fault, meaning literally a vertical vault planes slipping in the direction that I'm describing in this experiment, okay? It just happens to be that that earthquake happened last night. I was going to talk about this today regardless. But this is a sub-Rayleigh rupture, and this thing is moving a little less than the speed of shear waves in the medium. This front is moving at the speed that shear waves move in the medium, okay? All right. Now, I want you to look at the one on the right, and I don't know if you can see it. Maybe I can dim the lights just to see if we can see this a little bit better. See if I can make this darker. Like maybe just lights off for a minute. I don't want to put you to sleep, but I hope that you can make out this cone that my pointer, now that my pointer is pointing to it, I don't know if you can see that cone in the fringe pattern. Can you see this and this? And you see the classic S still here, okay? What this photograph is telling you is that the rupture is sitting here, okay? And it is traveling faster than the shear wave speed in the medium, okay? Here it was not, right? In this experiment, this is two separate experiments. This is called a sub-Rayleigh rupture. Sub-Rayleigh ruptures are your garden variety, if I can say that, earthquake. Most earthquakes are sub-Rayleigh ruptures, meaning the rupture travels slower than the S waves, okay? This one is a super shear. The rupture has outraced the S wave, and these are mock fronts. Literally mock fronts like you've read about or heard about. Acoustic mock fronts are the one you hear about with fighter jets, right? And things that go faster than sound in air. Sometimes we even see these vapor trails that they make, right? You've seen those in figures. This is not that. This is physical body and having a rupture that is traveling faster than the shear waves. It's not traveling faster than the fastest wave. The fastest wave in a body is the longitudinal wave. That's the sound speed in the object, right? This thing is not traveling faster than the acoustic waves. It's traveling faster than shear waves. There are two speeds in bodies, the longitudinal waves and shear waves. Shear waves are the slower of the two. This is outracing them. And this is a Mach front that is being shown here. Now, I'm trying to show you what I think is a wonderful application of interferometry in a research application. Okay, one, the high-speed camera is taking these frames microseconds apart, millionths of a second apart. Okay, you can train this camera to give you at 41 microseconds, this was it. Few millionths of a second later, you get another image and another. And if you look carefully, I'm not sure if the tape is visible. There's the corner of the tape right here. Okay, the tape I was talking about a few minutes ago. In this experiment, this S wave had not even reached the tape yet. Okay, and here's the fault parallel and fault normal laser vibrometers. These waiting for this thing to come by, and it hasn't arrived yet, right? The camera has the holistic view, and it says, here it comes, right? At 41 microseconds, there it is, okay? And it hasn't even, so this vibrometer signal has to be quiet at this time, okay? Now, in the super shear experiment, here's the tape, and look what's sweeping the tape at this instant of time. It's the Mach front. See, the Mach front is sweeping by, even ahead of the shear wave sweeping, okay? So this is an incredible contrast of two possibilities in nature, okay? That these fronts that rip open these interfaces normally travel a little slower than shear wave speeds in the medium, but every now and then, for reasons that are still being understood, they skip ahead and they travel faster. Okay, so this is a full field view, and then here are the vibrometer signals, by the way. So these are the, so notice how I label these red and green, okay? So red, green, so let's look at the sub-Rayleigh one first, okay? As I said, the more garden variety rupture, the one that happens more often, okay? What you see is the fault normal signal, which is the green, is dominant in its amplitude compared to what the fault parallel registers. Do you see that? Okay, the green clearly dips more in magnitude. We're not going to get into the signs of the motion right now, but I want you to see the signature of this rupture that the vibrometer sitting at this station picked up. Okay, now look what happens in the super shear case. Look how it flips. Look at the red signal. The red is the fault parallel now. The red is fault parallel. The green is fault normal. And you have this dramatic signature that the Mach front generates as it sweeps over the corner, okay? Now, there's theory, which we don't have time to discuss, that people have been working out since the mid-70s. People were predicting this before anyone experimentally saw it. It was predicted in 1976. Few more papers in the literature did theoretical predictions that such a scenario was possible. And in the earthquake community, people speculated, well, since you say it's theoretically possible, have we ever observed it? Has it ever? And people kind of wring their hands and said, well, I don't know, we don't have that much good data. It's hard to be waiting along these faults with all these sensors and waiting. Who knows where an earthquake is going to happen? Okay, it's not as easy as it sounds, right? To go and place these things all over the world, right? So the data was sparse. In the laboratory, Professor Razakis was the first to demonstrate this with model material, like I've just described. It doesn't mean that he proved it can happen in nature, but he proved it could happen in the laboratory, which had been predicted by theory, okay? So that's the connection there. And this is the two diagnostics. So I just love this example for you guys because I've been talking ad nauseum for 2 lectures about this interference problem and these laser vibrometers that have these point measurement. And sometimes I digressed into full field things. Okay, now I still haven't told you what this full field thing is. It's called photoelasticity, okay? Photoelasticity. And not every polymer is birefringent. You have to have a birefringent polymer that will aid in the creation of these fringes. These fringes are literally contours of maximum shear stress. That's literally what they are. That's why they light up when the S wave comes by, okay? So theory of that interferometer would show that these fringes correspond to fringes of maximum shear stress, okay? we don't have time to discuss photoelasticity. If this was a dedicated course in optical techniques, we'd go off and say, let's study photoelasticity now. So we just put that on the shelf, okay? It's an old technique that's been around for a long time. By the way, let's make a connection to DIC. So circa 2014, 15, Professor Rizakis decides, let's try DIC. Okay, I've been using this photoelasticity technique for years with my high-speed cameras. We got beautiful high-speed cameras. Why not buy the software? And so people started using that. And by speckling the surface, all of this has been seen now with DIC as well. Okay. The DIC ones, they look impressive, but they're all post-processed in the computer. To me, what was so elegant and beautiful about this is that this is the material speaking to us because it is stress birefringent polymer, okay? And it does something to laser light, okay? We don't speckle the surface and then process it. You could see this image on a sheet of paper, literally. I mean, you wouldn't see this because you couldn't see it fast enough, but literally before you do the experiment, you could already put a sheet of paper and see this, the static fringe pattern staring at you. You had a question, Ben.
In these situations, like they're both theorized, but we don't understand what caused it.
People understand. I'm kind of briefly going through this. I didn't want to digress too much. I mean, in 76, you know, it was predicted how you could trip the rupture to do this. And somebody did it with finite elements. Okay. And then he published a paper and he says, hey, look at this. Using finite elements, I can trick the system to going over this speed barrier that we've always thought was unsurpassable. For decades, people thought ruptures can never go faster than the sub-Rayleigh rupture speed. That's why I called it the garden variety earthquake, because I don't mean anything in a disparaging way. I just mean ruptures 9 times out of 10 are going to go at the sub-Rayleigh rupture. There are a great number of papers that have been written where people have now gone into models that say what trips the rupture to do this, okay? Asperities, heterogeneities, where it was traveling along and then suddenly some patch was just different enough that it tripped the rupture to go suddenly faster than this shear wave speed, okay? That would be too much of a digression. So in 76, probably nobody understood other than somebody who did it in their computer. Now I think people have a deeper understanding, but it's still a work in progress. Okay. Yeah.
Did he understand like what initial conditions could change?
Nope. Nope. That's the beauty of experimentation. You have a hunch because you've been doing some experiments in his history. He had been doing a different type of experiment. He had been doing an impact-driven mode 2 experiment. So for years, he and his students had done this. Okay. And then out comes this projectile out of a barrel, out of a gun barrel, which shoots out with this velocity v and impacts the top relative to the bottom. And he'd been studying this for years for the Navy, because the Navy cares about stuff like that, right? To a bimaterial interface, and now it's being dynamically sheared, right? So imagine the Navy gives you money to study something, sounds very practical, right? And I don't know, but follow my story. And then somebody in the earthquake community hears about your experiment. In this case, Professor Hiru Kanamori. He comes and visits ARIS and says, I see your papers on this. You guys see this super shear thing? Because they were seeing super shear with this. Again, they didn't know. They just saw it. Okay? This is the beauty of experimentation. You don't know what you're going to see until you do it, right? And sometimes experiments are duds. They don't show much, right? Okay, so then they said, can you nucleate it in a way that mimics more what the Earth's crust does? So we can't present this to the earthquake community, okay? They're going to run us out of the room, okay? And then they thought up with their grad student, okay? Can we just try to nucleate with some? Go try it. That's what your advisor is going to tell you if you're a grad student. Now go try it, okay? And that becomes like your thesis, okay? So I don't know how long it took this student to finally get this to work. Maybe it worked on the first try for all I know. I don't know, okay? But it's now become a very standard experiment. And today people do this with rock. They don't even do it with transparent materials anymore. They do it with real rock. But there are researchers in France who've actually done this rupture experiment with rock.
Does that mean that we're like now able to consistently give initial conditions that can reproduce the super shear rupture?
Yeah, we can do it, and then we see what nature sees. It doesn't always come. Sometimes it comes when we least expect it. It's kind of like physicists doing experiments. Do you think they see the hadron every day? Right? They do experiments and then, right? So, nature is still always a little mysterious, but at this point, they have some pretty good conditions that if they put enough pressure, if they roughen the surface in an appropriate way, they're going to get it most of the time in the laboratory. Nature is completely different, okay? The conditions in nature are whatever the Earth is. And so, interestingly, there's a list. I would say it's no more than 20 earthquakes in that list that the Earth sciences community have pretty much agreed were super shear based on data that was obtained in the field. Okay. All right, let me continue. So again, to bring it back to this class, it's an interesting thing, but I want you to see this is where experimental mechanics can venture. Okay. You can take you far afield. Okay. You're an experimental mechanician. Two things. One, Razakis understood fracture mechanics. He spent years understanding fracture mechanics, right? That's one. And then two, the experimental diagnostics. And those two things married together, and then out came some interesting things. Okay, now let me, there's more on that slide, but I think this is the key. Now, just note this signature, okay, for the record before we move on, okay? That's a very, very distinct signature of the super shear. Now, let me go to the next slide, move ahead here. This was an experiment that was matched to try to simulate a famous earthquake in Denali, Alaska, that happened in 2002. And the red curves are the famous pump station 10 record that was obtained. And the only reason we have these records, by the way, is because there's this transcontinental oil pipeline. If you go on a map, you'll find it. It runs north to south through Alaska. Okay. And these engineers in the early 70s, when they put this pipeline in place, knew they were passing through a strike slip fault. They knew it. And they were like, we better put in some good engineering mechanisms here to sustain lateral motion if the pipeline on either side of this fault gets displaced. Okay. They did a marvelous job because along came that earthquake in 2002 and not a drop of oil was spilled into the environment. Okay. But there was some stations there, fortunately, that also recorded the ground motion as the rupture swept. And this is how come seismologists knew, forget the blue curves momentarily, the red curves see a fault parallel dominant over the fault normal by a certain percentage, okay? Which is unusual. You never see that. And so then people did analysis and said that must have been super shear. This isn't a replication quote in the laboratory, okay, where we try to scale everything. And apart from this offset, which you'll notice, take a look at the fault parallel blue, the fault normal blue, and the fault vertical blue here, and how reasonably well laboratory record is following the phase modulations of this Earth record. It's not perfect. It can't be. This is a piece of Homelite 100, okay? And the other thing was in the Earth, okay? But the character of the fault parallel rupture. So this is the super shear rupture. You can see the Mach cone here, okay? That's the Mach cone, okay? And you can see it crossing. And this is the velocity signals that it gave in the laboratory. So this is, I think, a beautiful example of the full field technique, giving you fringes that give you a visual impression. Where's the rupture? Oh, it's right there. There's no disputing it. Nobody can argue where the rupture is. You can find that tight knot in the fringe pattern when you zoom in. You can find that tight knot, and then that knot, that the tip of the Mach cone then becomes visible, and you know exactly where that is. So it's spatially evident, and then the point measurement gives you this velocity signature as you swing by, okay? All right, so that's that. I'm going to shift gears now. This is a more traditional two-beam interferometer, but in this case, 4 beams were created from one so that 4 points could be probed simultaneously on this specimen. Okay, so imagine going through this little multiple beam splitter device. 4 lenses pass through the left side of the lens. They're focused on the specimen. They reflect. They come out the other side of the lens. And each of them is mixed at a beam splitter, right? With a reference beam in the way we talked earlier in this course, right? There's the reference beam, right? This is two beam interference happening by this beam splitter, what we've been talking about for two lectures, almost three, right? So, but you're getting four of them, okay? These are the fringes you get that you record on the oscilloscope. This is literally what you record, because this is not a commercial device. What the beauty of lab devices is you can see all the things, right? Because it's not a box that's just spitting out an answer to you. This is what's recorded on the oscilloscope as something unique happens in this specimen. And then you study the rupture in that specimen, okay? So this was studying a mode 1 rupture, this one, okay? This was studying this kind of a rupture, okay? You can see the crack in the specimen in the little cartoon, okay? And when this is impacted, that crack grows and it vaults forward. And the idea was, let's have these four beams trained just ahead of it so that we can measure the motion of the surface as this crack runs by. Okay. Okay. Let me show you guys. I've been dying to show you this. Juan here. Is Juan here today? Oh, good. So I'm going to answer a question that you had last time, which I had to kind of wave my hands around. You asked me about R and how R is defined in the K dot R, right? And so I'll give you a good explanation of that here, okay? What I want to revert back to momentarily is, remember I talked early on that two things can happen. Your two beams can cross like this, and they can have K1 not equal to K2. That's exactly what's happening in this diagram. I'm purposely wanting this beam to come in at this angle theta with respect to the normal, and I want this beam to come in at this angle theta with respect to the normal. And I want to look at that precise thing called K1 minus K2 dot R, which was in the interference formula. And I told you, when you make the two beams collinear and concentric, then K1 minus K2 dot R goes to 0 if the two beams are made to be perfectly concentric on each other, right? But if they're not, then we're going to say, what would we see here? Okay, that's literally what this is telling you. Okay, so I want you to imagine there's no moving specimen now. These beams are coming from wherever you'd like them to come from. And whatever's back there is just nice and quiet. It's the laser and some optics that made these two beams for us. Okay, that's all. And what we want to ask is no motion, but what happens when these two beams cross in space? Okay, all right, so this is the case. We're literally now examining this, what happens here, okay, in that interference equation that I'm not going to scroll back to, but we'll see it in a few minutes. Actually, it's here in front of us. I didn't realize it. It's right here in the lower right. Okay, I've circled K1 minus K2 dot R for you. And I want you to imagine that these phase terms, which would only change if surfaces are moving, these are quiet. Let's call them quiescent, okay? And this is what we're asking, what would we see? Watch how straightforward this is, okay? So the R that you asked about, Juan, in this case, is going to be a position vector, X in the X, which is going to allow us to dot the Ks along X in the X, because we're interested in seeing how the intensity varies along this X-axis, okay? So my answer to you the other day was kind of hand-wavy, because it depends on what you're trying to expose in your problem, okay? What projection are you interested in? In this case, we're interested in, hey, if I put a piece of paper here, or better yet, everybody knows these days what photoresist is, okay? I mean, photoresist is what's used to make every electronic circuit in the world, right? So if you had a plate with photoresist, light-sensitive resist sitting here, what would the resist see when these two beams cross? That's the point, okay? Guys, with me? Yeah? Okay. So now, watch this. It's very straightforward. We have to write K1 more precisely. We can't just keep calling it K1. Look how straightforward this is. There's your 2 pi over lambda, right? We've been talking about that. That's your wave number, okay? That's always there for K. And then we say cosine pi over 2 minus theta X component. Why? Because it's coming in at theta, and if this is theta, and I make a right triangle, then this is pi over 2 minus theta, right? So I'm getting its X component, and I'm calling it this, and its Y component. And notice Y positive is this way, down in my figure, right? Hence this minus sign for K1, okay? So K1 has two components. Cosine pi over 2 minus theta in the X hat. And by the way, X is positive to the right, so that's why that's positive, and then minus, okay? Similarly for K2, it's going to have a negative X component and a negative Y component because it's coming in from the right. It's got negative X, negative Y. Nothing could be more straightforward, right? Anybody confused about that description of K? Any question on that? We good? Okay, this is nothing but a vector decomposition of the wave propagation vectors K1 and K2. We have to do this because that dot product is begging to be taken, right? And I can't, the R is going to be X in the X, right? Because I'm interested in, if I pass two beams in space at that place, and that's the X-axis, then I'm interested in knowing what happens here, okay? What happens there? So I'm going to deliberately now take this dot product, K1 minus K2 dot R, where R is X in the X, okay? Watch what happens. It's really interesting. Okay, I'll just open up the slide so that we don't have to go through it piece by piece. If you do K1, okay, that's your K1, that's your K2, just being brought back. I'm just bringing it back. This is nothing new. We just developed this on the previous slide. And I'm saying, since we need their difference, might as well take it now, right? And you can see some things are going to subtract. If I go K1 minus K2, then you go minus a minus there, right? So these are going to kill each other, right? And then these are going to add, right? Minus a minus. But cosine pi over 2 minus theta is nothing but sine theta, okay? So get rid of the pi over 2 minus theta, put it back in terms of theta, okay? So your K1 minus K2 that we're trying to take right now has just become, in this problem, which is actually quite general, right? K1 minus K2 now just became, by the way we've rigged things, 4 pi over lambda sine theta, okay, in the X hat, right? The difference between the two became that, right? Now it's just a dot product, right? Notice this is in the X, and we're interested in dotting it with precisely something in the X, right? So we're really now just down to taking 4 pi over lambda sine theta in the X hat dotted into X in the X hat. And you can see what you get. It's the easiest derivation in the world. Look at what you get in the argument of the cosine function, because this whole thing, right, belongs in the argument of the cosine function, right? That was the whole point of doing this, right? That's the whole point, because in interferometers, the thing that changes is what's sitting in the argument of the cosine. So what it says is this. Here's a practical description of what this equation is telling us. Sitting on that x-axis is a fringe pattern, bands of light that go bright to dark to bright to dark to bright. How do we know that? Well, because cosine goes through 2 pi over and over again, right? As x changes. So that's interesting. It just says then that since this thing becomes 4 pi over lambda sine theta, and I'll just put x here, right? So every time this quantity, which is now our phase, okay, every time this quantity changes by 2 pi, I get a new fringe. I get a bright to bright or a dark to dark, okay? And so that's really interesting because you get to use that. Watch how you get to use that, okay? Watch this. So first of all, let's make a little cartoon that tells us what it is we would see, okay? When you cross these two beams, you'd get this diamond overlap region, okay? Because they, geometrically, you can see it, right? But the place where we've taken the dot product is along this line right here, right? X in the X, right? So we're watching the light field change along this x-axis. That's what this formula is telling us. Theta is fixed, right? Theta is constant in this problem. The two beams are just crossing at fixed theta. So theta doesn't vary. And so you just get these wiggles, okay? And these wiggles are nothing but every time delta phi changes by 2 pi. So you say 4 pi over lambda sine theta, call it delta x, is equal to 2 pi. So in other words, how much distance does it take before this phase changed by 2 pi, right? So that's a good thing to do, right? Cancel the pi's, and you get that delta x is equal to lambda over 2 sine theta. What does this tell you? This says you can rig this thing to have any periodicity you'd like in the laboratory. All you do is set the angle between the two beams, theta, and the wavelength is fixed. That's the laser wavelength. And you'll now get a series of bright bands. I'm going to show you how this is applied in 2 minutes, okay? You get a series of bright bands just like that along the x-axis. This is the basis for a bunch of interesting interference techniques, okay? Here's one in the fluids world that has existed for years, okay? Fluid mechanics people have taken advantage of this one for decades. Here's what they call it. They call it the laser. Here's the word Doppler again. Drives me crazy, okay? There's nothing Doppler in this problem, okay? Nothing, okay? But they call it that, and that's fine, okay? So here's a beam splitter that makes these two beams. This lens forces them to cross, okay? They cross in space. Here's a channel that has particles flowing in it in some fluid, right? But you know from this whole two-beam interference derivation we just did that inside that fluid, what have we just created? A stationary interference pattern that sits in space inside the fluid, a series of bright to dark bands of light, right? It's light. It's really there, and then there's a void of light, and it's a cosine transition as you go from this bright to dark, right? Well, these particles come streaming by, these tracer particles. They come streaming by, and with some velocity, they intercept dark fringes, and then they don't scatter any light, right? And then they suddenly hit a bright fringe, and then they scatter light, right? And then a dark fringe, and then they don't scatter light. So what have you just done? You've put a grid in the fluid medium. You've literally put an electromagnetic grid in the fluid medium. And as these particles come streaming by, back here, this lens and the light detector picks up these bursts. These bursts, because the light detector, all it knows how to do is pick up these bursts of light, right, that it sees. And these tracer particles light up and cut through these fringes, and they go bright, dark, bright, dark, bright, dark, bright, dark, as they come racing through, right? And so this device now picks up a frequency associated with the velocity of these tracer particles moving through this thing. So people measured fluid flow problems using this two-beam interference technique, and they still use it. Now, PIV is the dominant technique today, and this has now been relegated to more special applications, okay? But this is it. Literally, the velocity is the measured frequency on your oscilloscope of these light bursts that come by, divided by the fixed spatial frequency, fx, of these fringes. So many fringes per millimeter, okay? That was a neat trick, okay? There's another one, and I'm just going to end with this video that I want to show you guys. It's very short. There's not even any narration to it. I just want you to see the beautiful video animation that these people created. Just give me 2 seconds. Allow me to show you this, and I just want to impress on you how beautiful. And by the way, there are solid mechanic applications of this that are just as important, okay? Let me just go to a browser. Boom. Good. So you're seeing that projected. Watch. So you can just see it projected, and I can even skip ahead a little bit. Okay. So here they create the beams. Here come the two beams. Okay. They cross in space. Through the interference problem that we just derived, they create that stationary pattern in space, right? There's that volume. Now they're going to zoom in and say, see those fringes? Now our tracer particles are going to flow through those. Okay. And as our tracer particles, now they're going to even expand that even more, okay? And the idea is that tracer particles going through that fringe pattern. Let me speed it up if I have to, because I know there's more to this video. There's no narration to it, which is interesting. Okay, they're given a coordinate system. Here we go. So they light up. Here come the particles, right? Lighting up and scattering, right? Scattering light only as they pass through a bright fringe. And your photodiode now picks that signal up. This is new. This is the temporal frequency on your oscilloscope. New. And the velocity is nothing but nu scaled by the spatial frequency of those fringes. So it's a remarkable way to probe velocity flow in a fluid using this two-beam interference problem. So let me just stop there and say there's a rich assortment of problems that people have worked out over the years. Applications of two-beam interference. I've only shown you this fluid one today. There are solid ones too. So you could imagine, how do I measure in plane of a solid? Not my trick that I showed you with the corner of a tape, but how could I send light right down to a surface and get light to come back and somehow register the in-plane motion? Similar principles reign, okay? Similar principles are at play, all right? Starting next lecture, I'm going to transition the final string of lectures to the theory behind FEA, and that'll start on Wednesday, and I'll see you then.